Hello, friends. So, we are here with an amazing proof of AMGM inequality, and we are proving the AMGM inequality using Jensen inequality. Okay, so proof of AMGM is so famous and it's so common, but we are not here with a general proof of AMGM, and we are here with a very different proof of AMGM using Jensen inequality. So, welcome to my channel, Matt's Corner. My name is Pawan Pitlia. So let's start with the proof of AMGM inequality using Jensen inequality and a bit knowledge of calculus. Okay, so let me see if the voice is clear. Okay, it's clear. Let's move to the proof. Okay, so before moving to the proof, I want to tell you some things that are some prerequisites for this proof. Okay, the first thing is clearly what we are going to do, that is the AMGM inequality. So let's say AMGM inequality, all of you must have heard this, the inequality is for n non-negative real numbers, a1, a2, a3 till an. Okay, for a1, a2, a3 till an, we have the following inequality, that is a1 plus a2 plus a3 till an upon n is greater than equals to a1, a2 till an to the power 1 upon n. And the equality hold when a1 is equals to a2 is equals to an. And so on. Okay, so it's a very famous inequality. Okay, let us move to what is the Jensen inequality. Okay, so before moving to Jensen inequality, I want to give you knowledge of convex and concave functions. Okay, so let me give you knowledge of convex and concave function first. Okay, so let me give you knowledge of convex and concave function. Let me give you some idea about these functions. Okay, so what are concave functions? What are the convex functions? So first of all, concave functions are something. Let's say if fx. So I have a function fx, and that fx is concave. That fx is concave. If the double derivative of f of x, that is f double dash x, is less than 0, then we say that fx is concave, and we can draw its graph very easily because f dash x is the rate of change of fx, but f double dash x is the rate of change of f dash x, which is the rate of change of slope. Okay, so its slope is decreasing. The rate of change of slope is negative. That is, first its slope was negative. First its slope was increasing, and then it's going to be decreasing. So first of all, its slope was negative, and then it's moved to positive. That for convex, and if for concave, it's reversed. Okay, so what I have is graph is like that f double dash x is less than 0. So I have rate of change of slope. Rate of change of slope is negative. So what I can say that my slope was increasing, and then it goes and goes decreasing. So it's like this. So this we have a function, concave function, and for convex function I can clearly say that for convex function my f double dash x will be less than 0. Okay, and its graph will be something like this. Its graph will be something like the following graph, like this. It's for convex. Okay, so it's a basic knowledge that I want to give you. Now let us apply this knowledge in AMGM inequality. Okay, so we have this AMGM inequality. Now let us move to Jensen inequality. So Jensen inequality are two inequalities for different concave functions and convex functions. So first of all, let us move to Jensen inequality for the convex function. Okay, so we have f is a function from I, which is some set. Okay, so I have I some set that I can choose as per my wish, and this I two real numbers are, and this is a convex function, and that is f double dash x is less than 0, and x1, x2, x3 till xn are the points in I, that is my domain, and lambda 1, lambda 2 till lambda n are the real numbers in the interval 0 to 1. So all lambda i's are in the interval 0 to 1. So if lambda 1 plus lambda 2 plus lambda n is equals to 1, then I have that f of sigma lambda j x j j is equals to 1 to n is less than equals to sigma lambda j f of xj, j is equals to 1 to n. Okay, so it's for convex function. Let's see, we can expand this sigma. I can clearly write down this as following, that f of lambda 1 x1 plus lambda 2 x2 till lambda n xn is greater than equals to lambda 1 f of x1 plus lambda 2 f of x2 and till lambda n f of xn. So it's lambda 2 f of x2 and so on till lambda n f of xn. But generally, we are not known about the Jensen inequality in this form. What we are known is, generally we are known that when we put all lambda i's, when we put all lambda i's is equals to 1 upon n. Okay, so this will satisfy all the properties. It is sigma lambda I will be n upon n, which is 1, and it will be in the interval 0 to 1. So when I put the following, that form we remember, that is f of x1 plus x2 till xn upon n is greater than equals to f of x1 plus f of x2 till f of xn upon n. Okay, but generally this is the basic form, and this is the generalized form we can see. So for convex function, we have this thing greater than this thing, and for concave function, the inequality get reversed. So for concave function, the inequality get reversed, and that if x1, x2, x3 are the points in domain, it is I, then and lambda i's are real numbers, such as sigma lambda I is 1. Then I have that f of sigma lambda I xi is greater than equal to lambda I f of xi. Okay, so this is for concave function. This is for concave function. For convex function, you have seen that the inequality gets reversed. Okay, so let us move to our proof of AMG. Now, I am assuming my function f of x to be ln x. Okay, so what I am assuming that my function f of x is ln x. F of x is ln x. F of x is equals to ln of x. Now, what is this, convex or concave? So we can double derivative. We can find double derivative of the following thing. So f dash x will be 1 upon x, and f double dash x will be minus 1 upon x square. But we are concerned about the domain only. So nothing to check when x is negative positive, but x square is always positive. 1 by x square is positive, and its negative is also negative. So I get this is always negative. So I get f double dash x will be less than 0. And this implies that my fx is equals to ln x. That is, my ln x is a concave function. It's a concave function. Okay, so I think this must be clear that my ln x is a concave function. Now, if my ln x is a concave function, then what I can clearly say that if fx is concave, so what I can say that I can apply the following inequality. I can apply the following inequality. Okay, now I'm using my generalized form. Okay, so what I have is the ln of sigma lambda I xi is greater than equal to lambda I ln of xi. Okay, so I'm just putting the value of fx is equals to ln x in the following inequality, and I will get my AMG. Okay, so how will I do this? Let me first of all write my AMG inequality. Well, first of all, write my JENSEN inequality for concave function, that is the f of sigma lambda I xi is greater than equals to sigma lambda I f of xi. Okay, now I'm letting my function fx is equals to ln x. Fx is equals to ln of x. So what I have is that ln of lambda I x, that is lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 and so on till lambda n x of n. This will be greater than equals to lambda 1 f of x1, that is ln of x1 plus lambda 2 ln of x2 and so on till lambda n ln of xn. Now here I will put my all lambda i's is equals to 1 upon n for all I. Okay, so I'm putting the following thing. That is my all lambda i's I'm putting to be 1 upon I. Okay, so this will satisfy the following property also, that in this case I have this must hold, this will hold if and only if that all the sum of lambda i's are 1. But this is not satisfying, so I have put all lambda is equals to 1 upon n. So lambda 1 plus lambda 2 till lambda n will be n upon n, which is 1. Okay, so let's substitute that value here. So what I get is, when I substitute all lambda is equals to 1 upon n, the following inequality, what I will get is that ln of x1 plus x2 plus x3 till xn upon n, this thing is greater than equals to, this thing is greater than equals to ln x1 upon n, ln x2 upon n, that is ln x1 plus x2, ln x1 plus ln x2 till ln xn upon n. Okay, so this thing will be greater than or equals to ln of x1 plus ln of x2 till ln of xn whole upon n. Okay, so now I just will use the basic property of log, that is log of a plus log of b is log of ab, log of a plus log of b is log of ab. We'll use a property here. So here all the xi's will get multiplied and to form a single ln. Okay, so what I get from here is that the ln of x1 plus x2 till xn upon n. Okay, let me. Okay, so I have ln of x1 plus x2 till xn upon n is greater than equals to, I'm combining all ln and writing inside the product of all xi's, that is ln of x1 plus x2, x1 into x2 into xn, and it's 1 by n. Now again, a property of log, that something that is multiplied outside the log will get to the power of the product. Okay, so that is my one more property that I'm using, at k times log of a is equals to log of a to the k. Okay, this is property I'm using. Okay, so how will you get that I have that ln of x1 plus x2 till xn by n is greater than equals to 1 by n times ln of the product of all xi's. So I will get to multiply to this. I will get the following thing, that is my ln of x1 plus x2 till xn upon n is greater than equals to ln of x1 x2 till xn to the power 1 upon n. Okay, now the main thing now it's come to notice is the following, that if ln of something something is greater than ln of other thing, so what I can compute, what I can comment about it something something in the both brackets. Let's see. I have ln x. Let me see the graph of ln x. Okay, so if I see the graph of ln x, what I will get, that this is my graph of ln x. So this is my graph of ln x, and we can see that it's an increasing function. I'm talking about 0 to infinity, 0 to infinity, because that's my domain, because ln of negative is not defined. So I'm talking about this part. I'm talking about this part. You can clearly say that this part is constantly increasing. So if I take any 2 points, let's say one point A, other point, let's say B. So if I have that some ln of A, if I have that ln of A, I have greater than ln of B. So I can clearly deduct that its y coordinate is y coordinate of B function. When I put the value of function at FB, then that thing will be greater than ln of A. So I can clearly use that A is greater than B. Okay, so in the same thing, I will do the following thing. that I gave that ln of this thing is greater than ln of this thing, that all are positive. So what I can say that this thing is greater than equals to this thing, and hence putting the AMG inequality. So I have x1 plus x2 till xn upon n is greater than equals to x1 x2 till xn to the power 1 by n, and we have proved this inequality, and we have proved this famous inequality using calculus. So that's the power of calculus, and that's the end of video. So we can also write this in generalized form, that is sigma xi upon n is greater than equals to pi xi to the power 1 upon n. And in the next video, I will prove that this is greater than equals to that harmonic mean, that is. Okay, so that is all for today. Thanks for watching my video. Don't forget to like, subscribe, and share. Thanks.